Universal gravity is the concept of how are things attracted to one another. So if we think about the Earth and the Moon, why does the Moon take this path around the Earth, where it is constantly orbiting that? And so what happened is Isaac Newton understood Kepler's laws and tried to apply the concept of forces to this to understand why this is happening. Now, if we think about the moon, because the moon is traveling in a circle, we know that there must be some force that is directed towards the center. And towards the center is the Earth itself. And so what came of that is the concept of universal gravity, which that is that the force of gravity between any two objects with mass is going to equal a universal gravitational constant, mass 1, mass 2, over the radius squared. So this should seem familiar. It should look very similar to our force electric, which was K, Q1, Q2 over R squared. And so the concept of this is no different. This is the force between any two charged objects. This is the force between any two objects that have mass, right? This force is always going to be an attractive force because gravity only pulls things together. It's going to be the two masses. And when we're talking about this radial distance, we're talking about the distance between their center of mass. So if we're talking about the center of the Earth and the center of the moon, this would be that radial distance there. So conceptually, what we can see is that as the masses of the objects get bigger, the force is going to increase. So if the moon all of a sudden doubled in size, the force between the Earth and the moon would double. If the radius increases because it is on the bottom of my fraction, it's an inverse relationship. So as the radius gets bigger, the force actually gets smaller. So if the moon was farther from the Earth, say out here, then the pull that the Earth would have on the moon would be less, and the pull that the moon would have on the Earth would also be less. Please make sure we understand this applies to Newton's second law, or excuse me, Newton's third law, which Newton's third law is that for every action there is equal and opposite reaction. So this force not only pulls the moon into orbit, it actually pulls the Earth towards the moon as well. Those are equal and opposite forces. The thing is, the Earth and the moon are actually orbiting around their center of mass, which for the most part is probably right here. So this does pull, the moon does pull on the Earth. That's why we have tides. It also causes the Earth to wobble just a little bit, and where they're actually orbiting around that center of mass. But that center of mass is so close to the center of the Earth that we can just assume it is there. That's going to be the same concept, right, when we talk about our solar system. If this is the sun, which is substantially larger than the Earth, which is right here, they are actually orbiting around this position, which is not necessarily the center. So the Earth and the sun both orbit around that. However, the sun only wobbles, whereas the Earth orbits. The same concept can be applied here. We can find the force that the Earth is being pulled on by the sun, which is going to be the same as the force that the Earth is pulling on the sun, by that universal constant. If we simply know, right, the mass of the Earth, we need to know the mass of the sun and their radial distance between them. Okay. The other thing is this universal constant. This is found on our physics data booklet on page 2. G has a value of 6.67 times 10 to the negative 11. Its units then are going to be newtons meters squared per kilograms squared, right? And that should make sense because if we take those units up here, at the top, we're going to multiply by kilograms and kilograms, which is going to cancel out this kilograms. And we're also going to divide by radius squared, which is meters squared. And all that we would have left is newtons. Let's take a quick look at how we would compare the electric force and the gravitational force between two charged objects, right? So if we take a look at two electrons, they obviously want to repel one another, but they also want to attract one another based upon their gravitational components. So we're going to do electric in red, and we'll do gravitational in green. So the electric forces are trying to, the electric forces are going to try to repel. So there is some force electric, which is repelling both of these. There's also some gravitational force, which is trying to attract both of these. And those forces, right, that act on either object are going to be identical. I'm not saying the electric force is identical to gravitational. I'm saying that this gravitational and this gravitational are the same, and this electric and this electric are the same. Now, if we write out their equations, we get that their force electric is going to be K, Q1, Q2 over R squared, and their force gravitational is going to be G, mass 1, mass 2 over R squared. And if we think about this, you know, their charges and their masses are going to be different, but we're still going to multiply them together, right? And even though their masses are incredibly small, their charges are both incredibly small as well. Their radiuses are going to be the same, but their constants, right? This K value and this G value are incredibly different. So if we think about K, K is, again, Coulomb's constant, which is 8.99 times 10 to the 9th. Whereas G is going to be, like we just said, 6.67 times 10 to the negative 11. So if we think about this, which force, more than likely, is going to be larger? Well, that's based on our constants, And in reality, this Coulomb's constant provides a much larger force than gravitational constant. And so when we're dealing with things that are both charged and have mass, not most of the time, our electric force is going to overpower this gravitational force, right? And it's substantially larger, right? Like if we took the ratio of these two, it's multiple times larger than the gravitational force. So where we have electric force and they're repelling, there is some force that is attracting, but it's so small that we can ignore it for the most part and say that it is insignificant. So when we talk about universal gravity, we talk about gravitational fields. And this is no different than when we were talking about electric fields, just in terms of concepts. The application is going to be a little bit different, though. And really, a force field is a region in space where a body will experience a force because it is of its properties, such as mass for gravitational fields or charge for electric fields. It is simply a model to describe a non-contact force. So if we think about the Earth, there is a gravitational field around it, always pointing in. And unlike electric fields, which pointed in and out, or magnetic fields, gravitational fields are only going to be pulled in, right? Because we are simply being pulled into something due to its mass. There is no repelling due to masses. So gravitational fields are only in. And similar to electric fields, right? The more lines we have around an object, the stronger the gravitational field. So the moon might have a gravitational field that looks like this, whereas the Earth would have a gravitational field that looks like this, and the sun would have one with substantially more. Okay. Now, if we go back to when we were talking about electric fields was the force electric divided by my charge. That's one way that I could solve for it. Gravitational fields are going to be similar. So for a gravitational field, we're going to symbolize that with G. This is our gravitational field. We have solved for a gravitational field so far as force equals G over M. That comes from Newton's second law, which is simply mass times acceleration. And the acceleration that we experience in a Gravitational field is little g, and that's 9.8 times 10, or 9, just excuse me, 9.8. This is newtons per kilogram. Same as for electric field when this was newtons per coulomb of charge. This is newtons per kilogram. We know that a newton is a kilogram meter per second squared. And when we divide that by kilograms, we simply get meters per second squared. So that's the acceleration we experience, is the gravitational field of the Earth. Now, there's two ways that we could identify this g. We could also write this as g equals, what is the force of gravity? Well, we just found out that the force of gravity was g, mass 1, mass 2 over r squared over m. And what I'm going to say is that this mass, right, so this mass here would have been something that's in the gravitational field, right? So we have M1 and M2. M1 is going to be the Earth, and M2 would be the mass in the field. And for this M, that was this object here, so that's going to be mass 2. And what can happen is those two are going to cancel out, and we get that we can solve for the gravitational field of around any object with mass based on g m over r squared. So the gravitational acceleration, the gravitational field you're going to experience is based upon universal constant for gravity, the mass of the object creating the field, and how far you are from that object's center of mass. Lastly, we're going to look at orbital motion, and that's the concept of anything that is dealing with universal gravity. Usually we're dealing with celestial objects, right? Planets moving, satellites moving. And so if we think about, right, some satellite, which is out in outer space, it is orbiting around the Earth, or it's orbiting around whatever planet it is observing, right? And that orbital motion is caused by the gravitational force that it's going to experience around the Earth. Now, something to think about, this satellite at this moment is actually traveling in this direction. That's the velocity, and its force is pulled towards the center of the Earth, and so that is what pulls it into circular motion. And in reality, it is falling. It is falling towards the Earth because the only force acting on it is the Earth pulling on it. But because it's traveling in this direction, it's moving this distance fast enough that as it falls, so does the Earth, right? So if it's at this blue mark at time 1, and it's then at this blue mark at time 2, it has fallen some distance, but so has the Earth, has also fallen that same distance. And so even though it's being pulled towards the Earth, it's moving fast enough this way that the Earth falls away from it as well. So how would we deal with this? Well, the sum of the forces, right, would simply be that force of universal gravity, and that's going to equal mass times the acceleration. Now, this is going to be the mass of the satellite or anything that is orbiting, and this is going to be a centripetal acceleration. So let's then solve for this. Universal gravity, mass of the planet, we'll say, mass of the satellite divided by the radius squared. And again, remember, radius would be this distance. Okay? That's my radius. So if we talk about something is so high above the surface of the Earth, some height, we have to also include that radius of the Earth into that total. So like r, in this case, would be the radius of the Earth plus h. Okay, so just make sure you pay attention to that in the questions and how they're worded. Go back to this, though. This is going to be mass of the satellite, acceleration centripetal, which let's actually replace that with v squared over r. What can we cancel out? Mass of the satellite actually goes away. One of these r's goes away, and we can then rewrite this as g mass of the planet over r equals velocity squared. And so what we see then is that the velocity that a satellite has to travel to stay in orbit is simply based on the mass of the planet, not the mass of the satellite. So it doesn't matter how big the satellite is and the distance away from that. So that's why, right, this big heavy satellite and some little astronaut that's maybe doing a spacewalk, if they're both traveling at this velocity, v, right, they would both orbit the Earth. It doesn't matter about their mass. All that matters is how fast we are going, or the mass of the planet that we're going around, and how far away we are. If we then solve for v, right, that would be radical g, mass of the planet, divided by radius.